yesterday we left off on service factors. So again, in the book they're talking about the service factor using the horsepower, and that was getting the horsepower multiplied by 125% and gives you 37.5. I gave you something different. Is the size the overloads, using the service factor to size the overloads. On one of them, I put ambient temperature and I didn't put the service factor. Again, 40 degrees C or less, we use 125%. 1.15 or greater, 125%. If it's under 1.15, it's all other motors. Or the temperature is different, it's all other motors. Okay? Because sometimes you have the higher temperature rated motors that have a service factor of 1 because they're already working in the hot area. So sometimes they may not have the service factor, but they have the temperature. So always look at both. Always look at both. Okay, and again, when we do the service factor, when we're doing the thermal overloads come off the nameplate. Now we're going into a single motor. The way the book is, we're on page 192, the motor conductor. Motor supplying the single motor. And then it goes over, and then we're going to jump to the next page. So we're going to go from 13.3.1, and then we're going to jump to overcurrent protection, which is 13.4. First I want to do a single motor, the conductor size, and overcurrent protection. And then we'll talk about multiple motors or motors and other loads and their overcurrent protection. Now I want to separate it in two instead of going the way the book goes. We're going to separate it in two. Okay? Thought I heard somebody inside. Excuse me. Got hot out today. Hold on, let me turn the TV back on. We just had a glitch in the lighting. I don't even notice that the lights dimmed. The lights went out. Power went out, came back on. Had a surge. With this heat coming on, these generators aren't probably running up at 100%, so they weren't ready for all these air conditioners to kick on at a certain time. Okay, that's what happens. You know, so you're dependent on something, and then all of a sudden it changes, and you're not prepared for it. All right, where's my clicker? This is... Ya se vino para atrás. Tienes que prender otra vez el televisión. It says motor circuit conductors, and my wife, because everything went off inside. Motor circuit conductor is NEC Part 2 of the Article 430. Requirements vary by load. Circuit sizing varies by situation. So for most parts, a motor, where is it going? What is it detailed? Okay, so it says requirements varying by loads. Okay, so is it a single motor? Is it a feeder for multiple motors? Or is it a feeder for motors and other loads? What's other loads? Maybe lights, maybe something else, whatever else. You know, the motor is running, you may have other things that are on at the same time when the motor is running. But if the motor goes off, all these other things also go off. But they're on the same breaker, because if you're working on one part of it, you can turn the whole thing off with the flip of one breaker. And then rating and size of the motor, so it's all sized by situation. What's the situation? The situation may be multiple motors again, and then also the size of the motor. So whatever we're looking at. Not my day today. Nothing's working. There we go. Conductor supplying a single motor. Size according to NEC section 430.22E. So let me get put back around here. says conductors for an individual brand circuit supplying a single motor are sized in accordance with section 430.22. Single motor conductors are sized at 125% of the full load current depending on the code book. Okay, so now we go into, and we're going to look at this FLA that we've been seeing in the things, and then now we'll start adding the FLC. Okay, I always like to keep them separated, that way you know which of the two are. So the assignments that I send to everybody has the FLA, full load amps. Okay, what I'm going to talk about today is going to be the full load current, FLC. And the only reason I use the C is for the code book, because now we're going to use the FLC comes out of the code book. So our wire protection, our wire sizing, and our overcurrent protection come on out of the code book. So this is where we go to tables 432.48 to 432.50. Conductors that supply power to motors are not to be continuous use, may be used of size lesser current in accordance with table 430.22E. Okay, so 430.22E is where it's talking about the duty. Let me see if it's on here. Yeah, it's not on here. So it's talking about the duties. So if you have a 15-minute, 5-minute rated motor, 15-minute rated motor, 30 to 60-minute, then you have continuous loads where it's either the intermediate duty freight, passenger elevator tool, so it says 100. If you consider 112, continuous, it would be 140%. But again, a 5-minute rated motor, short time duty operated valves, rising and lowering rolls, 110%. 15-minute motor, 120%. 30 and 60-minute motor, 150%. Okay, and then it gives you the, that's a short time duty, then you have the intermediate duty, and then periodic duty, and the variant duty. So those are for various motors. And it would say on the nameplate. Okay, for the ones that I gave you, all of them under duty, all of them said CONT. Okay, so this means it's continuous. So if it's a continuous duty motor, we do 125%. Okay, so we've been working on, here, let me show. So we've been working on this 5 horsepower motor. Let me change the page here. So we got a 5 horsepower motor at 208, 230, 460, 3-phase. Okay, so this is the ones that I've been doing the examples on. That's that same 5 horsepower motor. I'm even writing the current. I don't care about the service factor now. Anything else that I gave you doesn't matter. All I need is a voltage, and is it single phase or 3-phase, and the size of the motor. So I got 5 horsepower. It's a 3-phase, so that means I would go to table 248. I would go to 248, 430. I'm 250. I'm sorry, 250, and then I would go. It's a 5 horsepower at 208 volts. It is 10.6. Okay, let me get a different color. At 230 volts. Oops, that was a 3 horsepower, sorry. Fix that. So at 208, I'm looking at 17.5. At 230, I'm looking at 16.7. I even looked at that wrong again. God, man. Tell you, it's not my day today. Now I wish I was using the whiteboard. Line of sight. Where's my ruler? Hold on. Let me get my ruler. My eyesight is off. Alright, so I got 5 horsepower motor going across. So I've got 16.7 at 208, 15.2 at 230, and 7.6 at 460 volts. Okay, so now that I have my amperages, okay, they were a continuous duty motor. I multiply this by 125%. .7 times 125%. Is 20.875. 15.2 times 125%. 19, 7.6 times 125%. Next we go to 310, 15, B, 16, and we find a wire. Okay, so I need a wire that can carry 20.8 amps. So if we're using THN or THWN-2 wire, we can use a 75 degree as long as we know our terminations. So in today's world, 90% of everything we use has got terminations at 90%. So if it's a 60-75, 60-75 at both ends, your termination at your disconnect, your termination at the breaker, or your service, or whatever you got, you can use the 75 degree. So for 20 amps, okay, I'm over 20 amps. So for this one, I'm going to say number 12. And then for these two, number 14. Okay, that's 19 amps. Looking at a 14 under 75 degree, it says 20 amps. Okay, so I can use it. Earlier we learned that it said, oh, wait a minute. Okay, that was that 246. It says that small conductors are 14, 15 amps, 12, 20 amp, 10, 30 amp. Okay, unless otherwise stated in this code book. This is where that otherwise comes in. So we can use that wire. Because this is at 20.8, I say it's over 20 amps. I say it's over 20 amps. That means that I gotta have 12 gauge. These are under 20 amps, so I can use a 14 gauge wire. Okay, now we're gonna go for, I'm gonna use a 3 difference. So my first one is gonna be, and then again, I'll put this in an example like I had it. So now we start going into, hold on, let me change this real quick. So it says full load currents, various motors, NEC tables are listed as full current motors on horsepower and voltage rating. So you go to the 430, 247, 48, 49, and 430, 250, you find the code. Okay, for the most part, you're going to find yourself in 248. It's a full load current of a single phase motor, and 430-250 full load current of a 3-phase AC motor. I've never installed a 2-phase AC motor. So for most parts, you're in two tables: 430-248 single phase and 430-250 3-phase. That's where you majority of time, all my installations, that's where they always come at. Regular motors that we put in thing. Let me change this real quick. Now it's talking about conductor supplying motors and other loads. I'm going to do that in a separate video. And conductors supplying multi-loads and combination loads, I'll do that on a separate video. I'm trying to keep everything separated. That way we don't get confused. So right now we're talking about a single motor. Overcurrent protection. Overloads not threatening brief. So let me go to the page real quick. In a normal course of the motor, occasional overloads are not uncommon. Motor starting, additional motor loading, and other conditions that create a high torque draw high currents, but pose no threat to the motor as long as they occur briefly and occur for a brief duration. Longer sustained overloads create abnormal heating of the circuit and can damage a conductor's insulation and result in motor failure. The current drawn by the motor is not constant. The lock rotor current is relatively high, 4 to 6 times at the running current. So when the motor turns on, the motor pegs out high. So that's what we did at the first, the starting currents. So using the letter code, that's kind of to give you an idea. Overcurrent protection device. So we have an overcurrent protection device. Guess what? It starts off where it's being fed from. So it comes out of a panel or a motor, an MCC, a motor control center. Okay, it may go over to a safety switch. Safety switch may have a motor starter on the inside. Once it has that motor starter, that's where our thermal overload's going. So we got to remember is when we're putting these breakers in, it's not an overcurrent protection. It's a short circuit protection, because it's either going to be 175%, 250%, or 300%. And then there's the other one, is the instantaneous strip breaker. I've never installed one. That's at 800%. Okay, so we have, these are different centers that we use. You know, you can have a regular disconnect. We used to have motor minder switches on some of them. Instead of having to disconnect, we just had a motor minder switch, because the main power and the motor controller was down on 2 floors down, 3 floors down, and an MCC, and this was up on the roof. So you had a switch to turn it off. So if you had to work on the motor, you have to have means to turn the motor off. So the overcurrent protection device is located at the motor control center, safety switch, combination starter, panel serving the motor. And it says the maximum rating of the motor, branch, circuit, protected device are listed in 430-52. Not on here. Let me go down a couple pages, see if it's on here. No. Alright, so it's not listed on there. That's not on here. You have a copy in your code book, in your textbook. It's on page 195, and it's 430-52. 430-52, and the code book is in page page 308. So it says the maximum rating setting of a motor branch circuit short circuit ground fault protected device. So it's called a short circuit ground fault protected device. It's not an overcurrent protection device. Same thing. Circuit breakers, types, fuses, settings. So we have a non-time delay, a time delay fuse, an instantaneous strip breaker, and an inverse time breaker. Okay, I have never installed an instantaneous strip breaker. I've used non-time delay rarely, but I've had used them a couple times. Time delay fuses and an inverse time breaker. There was a motor manufacturer, they wanted non-time delay. So in case it got to a certain point, it tripped out. Instead of handling the overload, it would trip out. So they wanted non-time delay, and that's the way they had it listed in their thing. So always look at what you're installing, and sometimes they'll tell you what they want. Okay, so a non-time delay, it's just like a, we talked about overcurrent protection already. So I'm not going to get too deep in it. Non-time delay fuse of this type holds 500% of the rating for 1/4 of a second. Time delay fuse carries 500% of the rating for up to 10 seconds. Instantaneous trip breaker. These circuit breakers trip instantly in the set range for about 3 to 10 times the base rating is reached. This type of breaker will only trip due to short circuit, not overloads. An inverse time breaker of this type are often used for commercial and industrial applications. The inverse time breaker will hold 300% overload for up to a minute depending on the circuit breaking rating and the system voltage. So a non-time delay can hold it up 500% for 1/4 of a second. And a time delay fuse, 500% of the rating for up to 10 seconds, and a breaker up to a minute. 300% up to a minute. Instantaneous more likely will trip right away once you start getting up there. It says the code alert. Next higher rating exception number 1, section 430.52C1. And you can find this in your book. Use the next higher standard size rating for possible settings when values for branch circuits, short circuit, and ground fault protection device do not correspond with the standard size or rating excuse me, of fuse, non-adjustable circuit breakers, thermal protective devices, or settings of adjustable circuit breakers. So I have 3 up here. So I'm going to go back a little bit. So my first one I'm going to use non-time delay. Second one I'm going to use time delay. And the third one I'm going to use an inverse time breaker. Okay, and then again I'll put this in. So that's my wire size. So I get the 16.7 multiplied by 300%. Okay, over here, $15.2. I'll multiply that by 175%. And 7.6. I'm going to multiply that by 250%. Okay. So, non-time delay fuse, time delay fuse, inverse time breaker. Okay, we're going to use the reading off the code book. So we're going to use the FLC, and I forgot to put this down. Okay, so these are my FLC, full load current out of the code book. FLA come off the nameplate. So and then I'm just going to multiply each one. Okay, where's the calculator? This seat's got to go on today. 50.1. You know what, I could go up to 60 if I want to, but I would put a 50 in. That don't hold, then I'll put a 60 in. Okay, 26.6, I can go up to 30. Code allows me. I'm at 19, I can put a 20 in. Code allows me to go to the next time. They don't make a 19 amp breaker. They don't make a 26.6 amp time delay fuse. And they don't make a 50.1 non-time delay fuse. They make a 50, they make a 60. So I would put a 50 in first. If that doesn't hold, then go up to 60. Okay. And this is how you find it. Very easy. Not a lot of different things. Always remember is when we're doing the thermal overloads, we use the nameplate rating. When we're doing the conductor and the short circuit ground fault protection, we're using the code book, the FLC, FL code book, or FL full load current, or the code book. That's why I like this. That way you can know which one switch. Okay. So tomorrow I'll do a video on motors, multiple motors. First I'll do multiple motors, and then I'll do multiple motors with other loads. Okay, so we don't get everything confused. We'll just work on one part and another part. We're jumping around the book just to make it easier to understand. So we're talking about a single motor, we'll stay with a single motor. Then we'll go to multiple motors, and then we'll go to motors with other loads. Okay, and close everything out there. Alrighty, y'all have a good one. If you have, again, if you have any questions, let me know. And stay out of this heat. Don't want you to get sick. There's plenty of fluids if you must go out, because it is hot out there.